All right, guys, in this video, we're going to go through everything you need to know about ligand substitution reactions. Okay, so there's a lot to unpack here. I'm going to go through it as concisely and clearly as possible, but there is a lot of information, so you're going to have to pay attention. Okay, this right here on the screen is directly out of the AQA A-Level chemistry specification. So I'm going to read through this quickly to show what you're going to learn by the end of this video. Feel free to pause, read yourself, or completely skip this section if you're not too bothered. I'm going to break it down throughout the video anyway in far more detail, so feel free to skip ahead. Right, so ligands. We're going to look at what they are. First off, you need to know what the monodentate ligands are: water, ammonia, and chloride ions. All right. Next up, you need to know that the ligands ammonia and water are similar in size and are uncharged. Okay. You also need to know that exchange of the ligands ammonia and water, or H2O, occurs without change of coordination number. So, for example, you're going to be using these in reactions with cobalt 2+ and copper 2+, and we're going to look at what is a coordination number. What does this mean? You also need to know that substitution reactions can be incomplete. For example, the formation of this guy right here, this copper complex. We'll look at that as well. You also need to know that the chloride ligand is larger than ammonia and water, and how this affects the substitution reactions. You need to know the exchange of the ligand water by chloride ions can involve a change of coordination number. Okay, we'll look at that and some example equations. You need to know Bidentate ligands. Okay, you need to know the names and the structures of both of these, as well as the formulae. Okay, ligands can be multidentate. You're going to have EDTA as our example. We'll look at that as well. Heme. All right, these last three bullet points are all to do with haemoglobin. Now, there aren't specific heme involving equations or reactions you need to know, but it's some extra bits of information that are really important, and they can throw in some random 1, 2, 3 mark questions to do with this, so I thought it's best place to include in this video. Right, as I said, there is a lot to unpack here, okay? A lot of people struggle with this topic, so let's try and break this down step by step and see what's going on. So, monodentate ligands. First off, we're going to look at what is a ligand and what is a complex. These are really fundamental concepts that you need to understand. Okay, so what is a ligand and what is a complex? Okay, a ligand is simply an atom, ion, or molecule which can donate an electron pair. Okay, donates electron pair, and what sort of bond does it form? A coordinate bond. All right, so let's write that out. Right, so that's the first definition written out that you need to know. A ligand is an atom, ion, or molecule that can donate a lone pair of electrons to form a coordinate bond. This part about forming a coordinate bond is not required for the definition, but it's really helpful to understand that concept. What is a coordinate bond? Exactly the same thing as a dative covalent bond. Okay, this is a year 1 concept. Let's say we draw out a bond here, okay, just a straight line to signify a bond. Let's say we have atom A and atom B, okay? One of the electrons is from atom A, one of the electrons is from atom B. Now, this is a typical covalent bond where it's a shared pair of electrons. Now, let's say we switch this up to be coordinate. You get rid of one of the electrons, and both of the electrons in the covalent bond come from one of the atoms. So, for example, both of these guys come from atom B in this example. Just using random letters here, but each of these would be a very specific atom in a proper equation or a structure. So it's exactly the same thing as a coordinate bond. Let's move on. That's some theory out the way. What is a complex? Okay, you're going to see this word thrown around all over the place when it comes on to transition metals and aqueous ions, all those sort of things. It's simply a central metal ion surrounded by ligands. Okay, so that's our second definition done. Really simple. Central metal ion surrounded by ligands. So I'm going to break down the monodentate ligands right now, and then I'll show an example structure of a monodentate ligand complex that we're going to have here. Now, I'm not going to focus on all of the shapes that you need to know. I'm going to do that in a separate video for all of the complex shapes and isomers. That'll be released soon, but for this video, I'm just going to focus on the actual ligand substitution reactions and everything you need to know for that. So let's cover the monodentate ligands. There's 3 you need to know. What are they? Okay, we've got H2O. What's the other one? NH3. And then lastly, we've got chloride ion. Now, these two right here, H2O and NH3, water and ammonia, these are neutral. Okay, they don't have a charge on them. These are molecules. Whereas this guy right here, the chloride, this is an ion and it has a charge. And we're going to look at how that affects the ligand substitution reactions in a little while. So you're going to see this word thrown around a lot, okay? Dentate and mono. So it's going to have mono is referring to one, right? It just means one. And dentate is referring to the number of coordinate bonds that that respective ligand forms. So you need to know monodentate or one coordinate bond. You need to know bidentate, two coordinate bonds. And you need to know multidentate, which is just anything more than two. For the AQA specification, it's going to be 6. And I'll break down what that example is. So let's say we look at water as an example. We're going to be forming, what bond are we going to be forming? Coordinate bond, okay? Because it's a ligand, right? So this is where the lone pair is going to come from. It's going to come from the oxygen. Very similar to organic mechanisms, right? The lone pair is going to come from the oxygen. Now, let's say we're dealing with an example of a copper central metal ion right here, copper 2+ as an example. What's going to happen here is this H2O molecule is going to form a dative covalent bond with this copper, okay? Now, you don't normally show it like this. If you wanted to show it specifically, what you would have here is the copper like this in the middle, and then you would have simply an arrow. And that's how we show a coordinate bond. You don't need to show the lone pair, and you don't need to show a curly arrow like in organics. This is inorganic chemistry. So we show a coordinate bond or a dative covalent bond simply with an arrow. So when we're dealing with monodentate ligands, you're going to be forming a different number of coordinate bonds, okay? And we refer to this simply as coordination number. Now, coordination number is simply the number of coordinate bonds involved in a complex. And as I said, I'll show an example in a second. But before I do that, I just want to briefly cover where the lone pairs come from. So you need to know this, okay? So in a water molecule, as I said, the lone pair is on the oxygen. In ammonia, the lone pair is on the nitrogen. And in chloride ion, it's pretty simple. There's just a lone pair on the chloride ion, okay? Now, how many coordinate bonds are able to form when we're dealing with water and ammonia? You're going to be dealing with 6, okay? You're going to be dealing with 6 coordinate bonds forming. Therefore, the coordination number equals 6. So let's roll this out. H2O and ammonia equals 6 coordinate bonds. So you will get a coordination number of 6, right? For the entire complex. Now, it's slightly different for chloride ions. Chloride ions are going to give you a coordination number of 4. And that is because they form 4 coordinate bonds around the central metal ion, okay? So let's look first off at some example equations when we're dealing with water or ammonia. Okay, let's start with these two, and then we'll move on to chloride after, and I'll explain why the coordination number changes from 6 to 4, okay? Okay, so let's look at some example ligand substitution reactions you need to know for ammonia and water. Okay, the examples given in the specification is for cobalt 2+ and copper 2+. Okay, so let's draw out the equations for both of these, see what happens with ammonia and H2O, and you should be completely fine if you just remember these two. So how do we draw a complex as a formulae? What you want to do is you want to start by opening a square bracket. Okay, now in physical chemistry, this would denote concentration, right? When you're doing a calculation, it would denote concentration. Whereas in organic chemistry, it's going to signify a complex, okay? An aqueous complex or an aqueous ion complex, whatever you want to call it. This is what it's showing you. Okay, so after the square bracket, you want to show whatever the central transition metal ion is. So let's use this example of cobalt and we'll chuck that in right there. Next up, you want to use rounded brackets outside of whatever ligand is present. So I'm going to be starting with a water ligand, and that's what you need to be aware of for these initial ligand substitution reactions, is you're starting with what's referred to as a hexa-aqua complex, okay? Hexa just meaning 6, aqua meaning water, okay? 6 water molecules right here. So rounded bracket, H2O, close the rounded bracket, and then you have to show how many of these ligands are bonded on by a lower subscript. So in this case, it's going to be 6, right? Then we close the square bracket. This is our complex. Are we finished? No. You have to show the oxidation state, or otherwise known as the charge of the entire complex. So if we're starting with a cobalt 2+, and we've got 6 water ligands, what is the charge on a water ligand? It's neutral, it's 0, right? So 2 plus 6 lots of 0 is still 2, so it's just going to be 2+. Okay, and what is the state of this? It's aqueous. All right, so this is our aqueous hexa aqua cobalt 2+ complex. Real mouthful, but that's what we're starting with. Now, we're going to be substituting all 6 of these water ligands with ammonia. Okay, I'm going to show that right here. So we're adding ammonia right here. How many did I say that we're substituting it with? 6. So we put 6 to signify 6 moles of this ammonia molecule right here. And this is also aqueous. Okay, this is all taking place in solution. So we're going to form our new complex here, our new cobalt complex. Now, going to be exactly the same thing. Square bracket, what is our transition metal center? Cobalt. What is our ligand? It's no longer water, it's going to be ammonia. Okay, so we're going to chuck that in our rounded brackets. 6 of these guys, okay? All 6 ammonia ligands substituted the water ligands. So we've still got 6 of those guys. What's the charge? What is the charge on ammonia? Neutral. Okay, it's 0. Exactly the same charge here. So it's still going to be 2+. Okay, and now the last thing we have to show on top of the states is the 6 water molecules have now been kicked off. Okay, so this equation is super simple to remember. Just remember 6 is replaced by 6, 6, 6. Okay, that's simple. All you have to get correct is the square brackets, okay, the rounded brackets surrounding the ligand right here, and then the overall charge on the complex. If you remember that, and you remember that it's fully substituted or completely substituted with all 6, you'll be completely fine. Now, what is the color change here? Okay, now a lot of students absolutely stress about this, including myself, guys. When I did my A-levels, I did the previous specification, okay, the pre-2016 spec, and I had to remember every damn color. You don't have to remember the cobalt colors anymore, okay? AQA has not been very clear with this. I see it in the textbooks, I see it on online resources and online YouTube videos. You don't need to know the cobalt 2 substitution reactions color changes, okay? I'll link a AQA specific teaching guidance document that specifically outlines that these substitution reactions involving cobalt 2+ color changes of reactions and products are no longer required. Okay, so I'll link that down below. If you're absolutely stressed out and you think you do have to learn them, you don't. Okay, so we're going to skip the colors here, but we'll look at the colors of the copper complexes, okay, the copper 2+. Let's look at that equation right here, and you have to know this. This is really, really important, and it's slightly different, okay? So far, I've been throwing around the word complete. That essentially means that all 6 ligands are replaced by all 6 of some other ligand, right? In this example, ammonia. What you need to be aware of with copper 2+ is we get what's referred to as incomplete ligand substitution. Okay, what does this mean? It just simply means that not all 6 of the water molecules or water ligands are substituted and kicked off. Okay, we're going to get partial substitution occurring. I like to use the word incomplete because that's the one AQA likes, but you can also say partial. That's completely fine. Now, this is always the case with copper, okay, when we use excess ammonia. Just keep that in mind. When we use excess ammonia, you're going to get this occurring. Now, I'm not going to go into too much detail regarding limiting and excess reagents. I covered all of that in my every observation and equation you need to know for aqueous ion reactions, okay? Whereas in this video, I'm just going to focus on the ligand substitution reactions. So all you need to know here is that for copper 2+, incomplete substitution occurs. So what is our equation here? We're going to start with exactly the same thing, but just swapping out this cobalt with a copper. Okay, so it's going to be copper. Let's draw this in red. Copper right here. Water molecule to start with. We're dealing with a hexa aqua copper 2 complex. Okay, what is the charge here? 2+, exactly the same. What is the state? Aqueous. Okay, all of this is aqueous. This is a liquid actually. I should have put liquid there. What are we reacting it with? We're not reacting it with 6 moles of ammonia because we're dealing with incomplete substitution. Only 4 moles or 4 ligands of ammonia are reacting here. That's also aqueous. Okay, so what complex is forming here? I'm going to draw it very similar. Now, we're going to have 4 moles of ammonia that came from this right here. Okay, so you're going to draw that in rounded brackets, signifying the 4 ammonia ligands. Okay, and there's 4 of those guys. Now, there's still 2 water ligands remaining because only 4 have been substituted or kicked off of the molecule. So it's going to be H2O here, 2, close the square brackets. What is the charge? Both of these are neutral, okay? They're both 0, so the charge is exactly the same. This is aqueous, okay? And then we're going to be kicking off 4 of the water molecules because 4 have been substituted by 4 ligands of ammonia. So that's going to be 4 H2O. And again, the state is liquid right there. Now, this is something you need to know from the spec, okay? What is the colors? What is the color change? And what is the coordination number change? So it's really important that you understand with these neutral ligands, there is no change in coordination number. Okay, what is the coordination number of this starting hexa-aqua complex? 6. Okay, there are 6 ligands. Each ligand forms 1 coordinate bond. So our total, 6 times 1, is 6. Okay, now over here, we have ammonia, but this is still only forming 1 coordinate bond per ligand. So we still have a coordination number of 6, okay? Now this one, this copper 2+ ligand substitution, the incomplete substitution, we're going from 6 right here to how many? 4 plus 2, still 6, okay? There is no change in coordination number. Now this switches up for chloride ions, which we'll check out in a second. But just remember, for ammonia and water, the neutral ligands involved in the specification, there is no change in coordination number. Okay, just keep that in mind. Right, with coordination numbers out the way, what is our color change going to be? This right here, this copper hexa-aqua complex aqueous, is going to be blue. Okay, it's a blue solution. Now, what do we change to here? What is the color of this complex? It's a deep blue solution. Okay, from blue to deep blue, making sure to mention that it's a solution. Okay, these are both aqueous. This is not a precipitate. All right, guys, so going back to our specification real quick, we've covered these monodentate ligands. I haven't explicitly said that these are similar in size, okay, the ammonia and the H2O, but we'll look at that right now when we delve into the chloride ion ligand substitution. But I have said these are uncharged. Now, we've looked at 2 examples of ligand substitution reactions, cobalt 2+ with the complete ligand substitution with ammonia and the incomplete ligand substitution with ammonia and copper 2+. So we've looked at that. Now, we've also looked at this right here. This is also in the spec, which I just mentioned, incomplete. Okay, really important that you know this. Next part we're going to look at is chloride ligands. Okay, how are they different to ammonia and water? And you need to know the equations for the examples of cobalt 2+, copper 2+, and iron 3+, and we'll look at that right now. All right, so as I said, from the spec, guys, we need to know copper, cobalt, both of those 2+, and then iron 3+ state. Okay, so let's draw these out. All right, so I've drawn these out. Now, when we add a solution of chloride ions, so for example, it could come from concentrated hydrochloric acid, right? When we add a solution of that to a solution of hexa-aqua complexes, whether it's copper, cobalt, iron, it doesn't really matter, you're going to get another ligand substitution reaction occurring, okay? The chloride ions are going to come in and substitute these water ligands, all right? That's just something you have to be aware of, and we'll go through the equations right now. Now, another thing you have to be aware of from the specification is, let's say we have our neutral ligands, right? NH2, where'd that come from? H2O and NH3, right? These are uncharged and very similar in size. How do we know they're similar in size? Their MR, okay? Their number of protons and neutrons. H2O, their molecular mass, or their MR, is going to be 16 plus 2, which is 18, right? NH3, what's the molecular mass of nitrogen? 14 plus 3 is 17, right? So these are very similar in mass and size. So let's look at chlorine now. We've got chlorine. Chlorine is a big boy, okay, chunky monkey. What is the mass of chlorine? The molecular mass of chlorine is 35.5. It's basically double these guys, all right? So in this case, with chloride ions, you cannot fit 6 around the central transition metal. There's just not enough space, okay? So the maximum that you can fit around a transition metal in these instances is 4. Okay, so just remember that. These are bigger, so that is the reason why you can only fit 4 chloride ion or chloride ligands around a central transition metal. So what does this mean then? We're going to get a change in coordination number. Okay, the number of coordinate bonds bonded onto that central transition metal is going to change, and we'll look at that right now, and we'll go through the different color changes. All right, real easy, guys. So 4 Cl minus. So plus 4 Cl minus plus 4 Cl minus. Okay, these are also aqueous. Now, what is this going to produce? It's going to produce another complex, okay, another aqueous complex, and we're going to get complete ligand substitution, okay? Even though we're reacting with 4 moles and not 6, because of the size and the charge difference, we kick all 6 of these off, replace it. We have a slightly different shape, which is tetrahedral. I'm not going to go into shapes in this video, but just realize the shape does change. But we're still getting complete ligand substitution. So let's draw out what our complex is going to be. Still got the central transition metal copper, and we're going to get 4 chloride ions surrounding this, okay? And the way you draw this out is slightly different, okay? We're not going to be showing the rounded brackets on the chloride ions. You literally just put Cu, Cl, or whatever the transition metal is, followed by Cl, close the square brackets, and then put the charge to the top right. Now, can you guys work out what the charge is going to be here if we've added and substituted these water ligands with the chloride ligands, which have a -1 charge? Okay, real simple here. We've got 2 plus 4 times -1. So that's exactly the same thing as 2 minus 4. So we're going to get an overall charge here of 2 minus. Okay, -2 charge right here. Now, all that's left to do is put in our state symbol and kick off all 6 moles of water ligands, all right? So we're going to kick off those 6 water ligands right here, and this is a liquid. Now, don't get too stressed out about the states. It's good to understand them. So in the color changes, you can say whether it's a solution or precipitate, etc. But normally AQA is pretty kind. Unless they say state symbols are required, you can leave them off. You should be completely fine. It says that in the mark scheme of the past papers, okay? Just make sure to include them if they do ask for them, which they definitely can, okay? Right, so I've drawn out our other equations that you need to remember. I've left one thing off on purpose, guys. What is the charge of this iron Cl4 complex? It's going to be a 1 minus, okay? Because we're starting with a 3 plus instead of a 2 plus, you're going to be dealing with a 1 minus charge, okay? Just keep that little caveat in mind and you'll be completely fine. So what are our color changes going to be? As I mentioned, you don't need to know the color changes for the cobalt 2 plus, but I'm going to include it in this video just in case you want to know, okay? So I might as well include it. So copper 2 plus, what does this start as? Exactly the same as it in our incomplete ligand substitution. This is a blue solution, okay? What is our product going to be? This CuCl4 2 minus is going to be a yellow solution. Yellow solution. All right, cool. Now I'm going to go over the cobalt really quickly. It's going to be pink. Pink solution right here. And what is our cobalt Cl4 2 minus? Blue. Okay, blue solution. Again, AQA specify you no longer need to know the color changes for the 2 plus cobalt reactions. So just keep that in mind. Don't have to memorize these. What is our starting hexa aqua iron 3 plus complex? Technically, this is purple, okay? Purple, violet, or lilac, okay? All of these colors are accepted. I like to remember purple because it's really easy. Now, something you really have to keep in mind here is even though the true color of this is purple, in solution, you normally don't get this, okay? This would normally appear as a yellow-brown solution. And the reason for that is it's been deprotonated once and you're left with Fe H2O 5OH. Okay, you're left with this, and this, I don't know why I drew it in purple, but this is a yellow-brown solution, okay? So even though purple is correct, you can also put yellow-brown solution, okay? Just keep that in mind. And what is the color of our solution right here? Yellow. Okay, another yellow solution forming here. So do your best to remember these color changes, and you should be all good to go. Now, something really, really important here you need to keep in mind, because AQA can try and trick you. If in a question they say solid copper chloride, so copper chloride right here, CuCl2, this is a solid, okay? If this is dissolved in water, if they say solid copper chloride is dissolved in water, it's not going to be this. It's not going to be CuCl4 minus, it's going to be this, okay? And that's because the CuCl2, it's because it's Cu2 plus Cl minus, there's two of these guys, so it's going to be CuCl2. When that dissolves in water, it forms this, okay? Just keep that in mind. They may try and trick you. They might not be that mean anymore, but I've seen it come up before, so just keep that in mind. Just remember, it's the aqueous Cu H2O 2+ complex. Okay, just keep that in mind. All right, guys, going through the spec, ticking it off step by step. We said that the chloride ligands are larger than the uncharged NH3 and H2O. Done. We've looked at the different substitution reactions that occur with chloride ions involving our cobalt 2+, copper 2+, and Fe3+, and how they have a change in coordination number. Okay, it goes from 6 to 4. Next up, let's look at our bidentate ligands. All right, guys, bidentate ligands. There are two you need to be aware of, okay? You need to know the formulae as well as the structure and the shape. I'm not going to go through the structure and the shape in this video. I'll save that for a different one, but you do need to know the formulae. So what are the two we need to know? First one is ethane 1,2-diamine. Okay, real easy one here. You're going to have an ethane in the middle, so a CH2, CH2. And then here we can see it's at 1,2-diamine, so it's just going to be an NH2 on either side. Now, in an equation, you don't really want to show the bonds, right? For the formula, you just want to show what atoms are present. So it's going to be NH2, CH2, CH2, NH2. Okay, that is our ethane 1,2-diamine. The other one you need to know is a charged ion, okay? Let's write that down here. Ethane dioate. Okay, ethane dioate, what does this look like? Real easy one, C2O4. What is the charge here? 2-. Okay. Now we'll save the shapes of these for another video because you need to know about isomers and shapes and bond angles and stuff like that. But for the sake of the bidentate ligand substitution reactions, what do you need to know? Bi, okay? What does it mean when it's bidentate? It means that every single ligand that is present is going to form two coordinate bonds, okay? Bi meaning two. So let's look at this first one, this ethane 1,2-diamine. Where are the lone pairs that are going to be donated to form the coordinate bond? There's one on this nitrogen and one on this nitrogen. All right, pretty simple. On this one right here, I have to kind of show the shape really, don't I? So it's going to be O, C, double bonded carbonyl group right here, another carbonyl group, and then an O, okay? The lone pair is right here, okay? So this is going to go on, form a coordinate bond with the central metal, whatever that may be, and it's going to form two coordinate bonds per one ligand. All right, so just keep that in mind. All right, so let's draw out our equations that you need to know. Again, starting with a hexa-aqua complex, real simple stuff. I'm going to start with a copper, but you can swap this out for any metal. It doesn't specify in the specification which metals are going to be used as an example, so I'm just going to use copper right here. Now, 6 water molecules or 6 water ligands, 2+ charge right here. This is going to react with how many ligands? All right. If we're getting complete ligand substitution occurring, all 6 of these water molecules have to be kicked off and substituted. So are we going to react with 6 moles of this guy? No, we're not, okay? If we reacted with 6 moles of this, you're going to get 12 coordinate bonds forming. That's way too many, okay? Each molecule is forming 2 coordinate bonds, so we just have to halve the number of moles. So it's going to be 3 lots of this. Okay, so I would put 3 moles of the NH2, CH2, CH2, NH2. All right, easy peasy. I'm going to leave off the states here, but this is all aqueous. And then this is going to form our new complex, okay? What is our complex going to be? You literally just have to change the water inside this bracket with this right here and change the 6 to a 3. Charge stays exactly the same in this instance because this bidentate ligand is neutral. So let's draw that out. We're going to have our square bracket, copper, NH2, CH2, CH2, NH2, close rounded bracket, 3 of those guys. Charge stays exactly the same. All right, easy as that, guys. All 6 water molecules have to be kicked off. Okay, not too bad. That is our equation that you need to know for the bidentate ligand substitution involving ethane 1,2-diamine. Now, let's look at ethane dioate and see how it's slightly different. Right, so I've moved things around slightly because I realized I wrote this equation under the ethane dioate, but that's not what you want to do, okay? So let's start with our same example. I'm going to use copper again. So copper, hexa-aqua complex, 6 of those guys, 2+. Okay, now we're reacting it with ethane dioate. This is all you have to write, okay? You don't have to write it out in any other format. This is completely fine. How many moles of this? Exactly the same, okay? Going to get 3 moles. 3 moles because each ligand has 2 coordinate bonds. I know I'm repeating myself, but repetition sometimes really helps out in making sure that you remember that these little caveats of information, okay? What is this going to form? Real easy. Replace the water or substitute the water with this. That's why it's called a substitution reaction, okay? Pretty simple stuff. So let's draw this out. Copper, rounded bracket. We're going to show our C2O4. Close rounded bracket. How many of these guys? There's 3. What is the overall charge? Now, this has a 2-. You don't want to put a 2- in the rounded brackets or outside the rounded bracket, something like that. You do not want to do that because now this is a complex. Okay, this is an ion. This is a complex. So you want to show the charge outside the square brackets. So what we're doing here is we're going from a 2+ and we're minusing 3 lots of 2-. Okay, so 3 lots of 2-. Exactly the same thing as 2 minus 6, which equals -4. So this charge is going to be 4-. Again, same thing, we kick 6 water molecules off. All right, simple as that. That is our other equation that you need to remember. Just remember that they may ask you to swap this out for a different transition metal, iron, chromium, nickel, whatever it may be. They can test you on different things when it comes to this. Now, if I was to ask you, is there a change in coordination number here? What would you say? No, there is no change, okay? We're going from a coordination number of 6 to a coordination number of 6, okay? Even though there's only 3 ligands here, each ligand forms 2 coordinate bonds. So we have 3 times 2, which is 6, okay? Exactly the same coordination number here, nothing changes. All right, so we did that. Not too bad. Let's look at multidentate ligands. Okay, this guy right here, EDTA4-. All right, so I'm going to draw out EDTA4- and show you what it looks like. You don't need to remember this shape, okay? You just have to remember the formula EDTA4-. They make it pretty easy for you. But I'm just going to draw it out so I can show you where the lone pairs come from to form those coordinate bonds. All right, guys, so this is our EDTA, right? EDTA4-. That's all you need to know it as, EDTA4- when you're writing out your equations. This is way too complex, okay? So where do our coordinate bonds come from? There's a lone pair right here, lone pair right here. There's a lone pair on the nitrogen as well, on both of these nitrogens. And there's a lone pair on the other 2 oxygens. Okay, there's a lot of symmetry going on here. If you split this molecule in half, you can see perfect symmetry. Okay, so each nitrogen and oxygen has a lone pair, ignoring these ones, okay? The lone pair does not come from the carbonyl. It comes from the negatively charged oxygen right here. So if I showed you this structure and I said, okay, how many coordinate bonds is this going to form? It's going to form 6. Okay, so even though we have 1 ligand, each of these EDTA4- ligands is going to form 6 coordinate bonds. So in that case, we're going to get complete ligand substitution occurring with only one ligand. Right, so let's draw out an example equation here for this ligand right here, this EDTA. So again, I'm going to start with copper as my example. 2 plus, right? This is our hex aqua complex plus EDTA, okay? That's all you have to write it as. I keep repeating myself, but that's literally all you have to do. EDTA 4 minus, pretty simple. Now, all 6 of these water molecules is going to get kicked off because we're dealing with 6 new coordinate bonds right here, okay? So our complex is just going to be copper, rounded brackets, replace the H2O with the EDTA. Okay, close rounded brackets, square brackets for the complex, and then the charge has changed, okay? 2 plus minus 4 is just minus 2. So we're going to have a 2 minus charge right here, and then all 6 water molecules got kicked off. All right, this is our equation that you need to remember. Really simple one. Again, this can be swapped out for a different transition metal. Just keep that in mind. Therefore, the charge on the overall complex may change. For example, if it's an Fe3+. Okay, just keep that in mind. All right, not too bad. We've covered the multidentate ligand. That's everything you need to know. It's not too complicated there. Right, so let's move on to our last 3 bullet points. This is all about haemoglobin, okay? Heme and haemoglobin. Not really involving any sort of substitution reactions here, but it still involves coordinate bonds, so I thought it was some useful information to throw in at the end of the video. And then after that, we'll go on to some practice questions. So if you don't really want to know about heme, feel free to skip ahead. Do some practice questions, okay? It's really important that you revise, do some practice questions, test your knowledge, and do some active recall. So I'm going to go over this super quickly. It's all you need to know, guys, is straight out the specification. There's no more crazy information that you need to know. So I'm going to read this out right here. So heme is an iron 2 complex, okay, an Fe2 plus complex, and it contains a multidentate ligand. All right, next up, oxygen forms a coordinate bond to Fe2 in hemoglobin, and this allows oxygen to be transported in the blood. Okay, that's literally all you need to know there. It doesn't get more complicated. They're only going to be able to throw in some 1 or 2 mock questions for this, okay? Next thing is carbon monoxide, okay? Carbon monoxide is incredibly toxic to mammals, okay? Humans as well, because we're mammals. But carbon monoxide can form a strong coordinate bond with hemoglobin, okay? And it can displace oxygen, okay? It's stronger than the bond that hemoglobin makes with oxygen, okay? So it can replace it, can build up in your blood and kill you. All right, pretty much that. So it's incredibly toxic. And you do need to know this, okay? It can replace oxygen inside the hemoglobin molecule. And why is that? Because it forms a stronger bond, okay? If you guys do biology, you'll be fully aware of this. All right, some test yourself question, guys. Going to start with some easy ones here and then move on to some slightly more difficult ones. So first one, what is a ligand and what type of bond can it form? So pause the video, work through these questions, see if you get them right. So what is a ligand, guys? The definition you need to remember is that it's a molecule, atom, or ion that can donate a pair of electrons to a central metal ion, okay? All right, that's the first mark. What type of bond can it form? Pretty simple, coordinate bond, okay? Not too bad. 2 marks in the bag. Question 2. Describe what it means for a ligand substitution to be incomplete and give an example equation for this type of reaction. Okay, so I may not have explicitly said this in the video. Okay, so incomplete ligand substitution is when one ligand is only partially replaced by another in a complex. Okay, not too bad here. What is our example equation? There is only one that you need to know involving copper 2 plus. So let's draw that out right now. Done, guys. Okay, real simple one here. Just remember 4 moles of ammonia, 4 moles of water are kicked off and substituted. Okay, and this is the incomplete ligand substitution reaction you need to know. All right, question 3, guys. Ethyl 1,2-diamine is an example of a bidentate ligand. Name a different bidentate ligand and write an equation for a reaction involving this ligand and a solution containing aqueous iron 2 ions. Right, so can you remember what the other bidentate ligand is that you need to remember? Ethane diurate, okay? Ethane dioate. And what is the symbol for this? C2O4 2-. Okay, so let's draw out an equation for this reacting with an aqueous ion 2 ion complex and see what's going on here. All right, guys, easy as that. Remember, we've got 3 moles of the ethane dioate reacting here because each one of these ligands forms 2 coordinate bonds. So 6 of these guys is replaced by 3 of these, but our coordination number does not change, okay? What does change is our charge, okay? 2 plus 3 lots of 2-, so 2 minus 6 is 4-, and that is our change in charge or oxidation state, whatever you want to call it, completely fine. And that is our example equation from this question. Hopefully you guys got that right. All right, guys, last question here, question 4. Write out the equation for where a hexa aqua copper 2 complex reacts with conc HCl and explain what happens to the coordination number. All right, so let's draw out our equation here using copper 2+. All right, cool. I've written out our equation here. 6 water ligands are kicked off and replaced by 4 chloride ions. This is still complete ligand substitution, okay? But we're getting a change in coordination number. So what we have to do next is explain what happens to the coordination number. It changes from 6 to 4. And we have to explain it, okay? Explain is our command word. This just describes it. We're just changing it from 6 to 4. Why is that the case? It's because chloride ions are larger, okay? And that is why only 4 are able to fit around the central metal ion. All right, that would be our answer there. That was our final question. Let's go back to our specification, tick things off. Last 3 things here was just to do with haemoglobin. That's really easy. Just memorize those fine details and you'll be completely fine. I put a ton of time into this video, so I really hope you found it helpful. If you did, like the video, it really helps the channel out. If you have any questions, let me know down below. And remember guys, I have not included the shapes, the bond angles and the isomers of these complexes. And I haven't included the chelate effect, okay? The chelate effect is more to do with entropy, Gibbs free energy, and enthalpy change, and it's to do with the stability of these complexes, but I will save that for a different video. This video was just focused on the ligand substitution reactions themselves, okay? So keep that in mind, realize that you have to learn this, go through the specification yourself, cater it to you, tick it off as you go. Do practice questions, okay? All of this is incredibly important. Best of luck with your revision and upcoming exams, guys. Until next time, peace.